This is the video instruction for the laboratory magnitudes and distances, specifically how astronomers will use the information of apparent magnitude and parallax, which are both measurable, to calculate the distances to the nearby stars, okay? And the key is this is only workable for the nearby stars. We cannot apply the parallax methods to stars that are very, very far away. And that's because the parallax angle will be simply too small, even for some of the most powerful telescopes, okay? And the workable range for the current limit is about 30,000 light years, only about 1/3 the size of the Milky Way galaxy. And so the parallax methods is only really good for the nearby stars. But this is extremely important because by establishing the property and the distances to the nearby stars, we can use this as a foundation to extrapolate and expand into other methods to figure out the distances and the property of the stars much farther away. And so the parallax methods really give us a sort of a foundation of astronomy to figure out a lot of information about the nearby stars, okay? And so this lab, we are going to pretend to use Stellarium and to figure out the information of apparent magnitudes and parallax to figure out distances, okay? So astronomers, of course, will measure these things, but in this lab, we are going to pretend that we are using Stellariums as astronomers will use telescope and do these measurements. And this is the idea of a parallax, and that is if the Earth is orbiting around the sun, okay? And so 6 months apart will give you the best two different positions for observing the apparent shift of a nearby star against the distant stars, okay? So in July, you will see, for example, the nearby stars here, but 6 months later, the maximal opposing distance from July, like in January, then you will see this star originally here in July shifted in terms of viewing to this position, okay? So against the background stars, the nearby star will shift. But as explained in the lecture, this angle is actually twice the parallax. So whatever the astronomer measure, this shift from here to there, divided by 2, okay? But you don't have to worry about that. In Stellarium, you simply take the parallax as it is already measured and calculated, okay? And so that's the idea of a parallax. It is the apparent shift in the position of the nearby stars against the background star over the maximum periods of opposition, right? That's 6 months apart for us. Okay, so again, this only apply to nearby stars. And you will use this, this information, okay? You will use this information of the parallax angle. I mean, the parallax actually is measured as an angle. And so the distance to the star right here, if you're good in geometry, is simply, you know, this is basic, like a sine function, right? And so, so we use a so-called small angle approximation in trigonometry, but we don't go into that. But basically, for almost all the stars that basically all the stars that we're going to work on, not almost all, basically all the stars, we can just use this very simple formula, 1 over parallax angle, simply whatever it is that is measured and observed, take 1 over that, and that gives you the distance, okay, the distance to the star, okay? And the key word, okay, here is the key point to understand is this formula is simply written in this form, provided that the units are correct, okay? So this is a simplified and standardized formula, and the parallax here has to be in arc seconds, okay? Has to be in arc seconds. And I will point out right now that the parallax angle given in Stellarium is milli-arc second, milli-arc second. Okay, so you have to do that conversion to arc second, and I'll explain that very quickly in a table. And once you do that, 1 over the parallax angle in arc second, you will get the distance, and that number is in parsec. So this formula, you have to, again, be careful that parallax has to be in arcsecond, and the distance that you get will be in parsec, okay? And so how do you do this, lab? It's very simple. And so let's fire up Stellarium, and I'll show you. Yeah, let me turn off and pretend we are seeing the evening mode. And so let me just pick out any small star, any stars, not any small stars. Let's say Vega, which is one of the nearby stars, okay? And so you will see a lot of information here, and we talk about magnitude, okay? And Vega happens to have a apparent magnitude of 0 just by coincidence, okay? So for Vega, the apparent magnitude is 0.0. It also gives you absolute magnitude 0.57. But however, this is not, what you will use. Okay, you will pretend you don't know this, okay? Because we are first making observations. We measure what we know, which is apparent magnitude. You of course, as an astronomer, cannot measure absolute magnitude. That has to be calculated, right? But it also gives you distance in 25 light year. You also need to pretend that you do not know that right away. But what you can measure is the parallax, okay? So the two information or two data points that you can measure is apparent magnitude here and the parallax angle here, okay? So you see magnitude of 0 and then a parallax of 130. And notice this, MAS, 130 MAS. And so in table 1, what you're going to write down is what astronomers can observe: apparent magnitude and parallax, apparent magnitude and parallax. You can write down the distance from Stellarium in light year, but you will not use this information. Okay, but it's good for you to know this information, so at least for this lab, that you know you do it right. And you see here in gray, okay, column number 5 and 6, you will calculate, okay, column number 5 and 6 from this previous columns, okay? So again, the distance you calculate from the parallax using equation number 1 over p. So whatever you read from Stellarium here, you write it down here and take 1 over p. So let me give you an example. In Vega, remember, we just read this, and the information was 130. Okay, remember the parallax here was 130 MAS. So let me write this. So the Vega apparent magnitude is 0.0, and the parallax is 130 MAS. But remember, this is milli-arcsecond. This is not arcsecond. You have to convert that into arcsecond. And so basically milli is 0.001, right? It's milli. Milli is 1,000th. Okay, so you simply do a conversion divided by 1,000. So that gives you, instead of 130 MAS, you write down 0.130 arcsecond. Okay, so you understand this is arcsecond. Okay, so make sure you understand this part. You have to convert this. And the distance is simply 1 over 0.10, 1 over 0.130. Okay, so whatever the number you get here, that will be in parsec. Okay, so again, you calculate the distance by the observed parallax. Okay, let me turn off Stellarium. All right, and of course, you can convert the distance from parsec to light year. That you multiply by a number directly. You have to find out that conversion factor. There's something like 3 point something. Okay, so whatever the number you have here, multiply that by that conversion factor again from parsec to light year, and you can easily find out this on the internet. You have to do that on your own. Okay, so from parsec to light year. Okay, you can do that right here. Now, how do you know you do it right? Well, you can check, right? Stellarium gives you the light year right here. So just to compare this with that here. So compare the number you actually got from doing the, doing as astronomers would by getting from parallax, from literally, what the Stellarium is really telling you. And these two numbers should be very close, right? Because, that's how they do it. So make sure that you can use this to check your work, okay? But again, you get apparent magnitudes and parallax, just like you would if you're an astronomer, and then from the parallax, calculate the distance. Again, these are nearby stars only. Once you have that information, then what you're going to do is you're going to go to equation number 2. Okay, there's equation number 2 and equation number 3. Typically for most stars far away, we have to figure out the distance using equation number 3. But for the nearby star, we're going to do the other way, and that's because we actually know the distance. Okay, for the star far away, we don't know the distance. We cannot use parallax methods. We have to use other ways to figure out other information, especially absolute magnitude, and then figure out the distance. And so nearby stars and far away stars are actually done differently. So for the nearby stars, because we have the apparent magnitude little m, and we have the distance d, okay, using parallax, we can measure that. These are both measurable, and that's what science is. We measure whatever we can. We don't go around guessing, right? Whatever we can measure, we measure them directly. So once you have little m, once you have d, then you can use this formula to figure out the absolute magnitude. Okay, so for the nearby stars, this is the wonderful thing. We can use a very simple, straightforward parallax method from which we can figure out, literally calculate directly, without other guesses and so on, absolute magnitude directly. And that's why establishing this foundation of the, of the star property like distances and all that for the nearby star is extremely important for doing astronomy, because we need this in order to expand to farther distances. Okay, and so once you have little m and a d, then you will calculate the absolute magnitude. Okay, just follow equation number 2. So use table number 1, okay, column number 1. So you will have, remember, you have apparent magnitude, and then you have distances, right? You have column number 2, column number 2, and column number 5. So you have that information. You use this formula for each star. You figure out the absolute magnitude. Follow this formula, and it's very simple. And one thing to point out, read the instruction here. This log here has to be log of base 10. Some calculators actually would say log, but it's actually natural log, right? So just by looking at a calculator, and with a button that says log, it's actually difficult to know which one it is just by looking at it. So just do a test. What you do is you type in 10 and take log of 10. If it gives you 1, then that's correct. That is the correct log function you're going to use. That's log of base 10. But if it's not log of base 10, okay, then it will give you a different number. It will not be 1. That will be natural log. Okay, so make sure that your calculator is log of base 10. Now, if you don't have a calculator, of course, just use google.com, just type log, and then use the online calculator and then follow the instruction, right? Right now, the internet is very convenient. And so this is how you do this lab. So figure out, using Stellarium, figure out apparent magnitude, measure parallax. From parallax, get the distance. Once you have that in table 1, follow equation 2 to calculate capital M, absolute magnitude. Okay, so that is the instruction.